Today in Capeggi's Corner, we're going to look at scatter plots and lines of best fit. Now, again, you did some of this probably in algebra. So we're going to look at some things. Some of the terms might be new. So we have a bivariate data. That's a data with two variables, right? Two variables. That's the prefix bi. Scatter plot. It shows the relationship between a set of data with two variables graphed as ordered pairs on a coordinate plane. Okay, so we can look at the relationship between those. The line of best fit, the biggest thing with the line of best fit is I like to say it's called the line of best fit, not the line of exact fit. So we're doing the best we can. It's not going to be perfect when we draw them. It's not going to be maybe the same as the person sitting next to you, but it's the line of best fit. When data points on a scatter plot lie close to a line of best fit, or sometimes we call that a trend line. What's the trend? Can model the trend. So if you look at our examples for scatter plots, we have one that's positive. It's a positive correlation, a positive slope. As x goes up, the values in y go up as well. Negative correlation, again, just like a negative slope. As the x values increase, the y values decrease. And you can see things like no correlation at all. And that could be something with, if your x-axis was something like, the color that students had on today, that depended upon what they ate for lunch. Well, they have no correlation at all. That's something that has no correlation. One has nothing to do with the other. Now we have steps that we're going to go through using this linear function in our scatter plot. So if you need to pause this at some point to kind of catch up with your writing, but I will kind of walk you through it. Step one is viewing the scatter plot and determining the independent and dependent variables and the type of correlation. Is it a positive? Is it negative? Is it no correlation? Then you're going to kind of observe the line of best fit. You're going to draw one and see how it goes the best you can if it's not already drawn for you. Then you're going to look at 2 points on the line of best fit. Now, they may not be the points that they were given to you, but look to see which points will fit, easy to work with, and you're going to use those to write an equation of the line. Now, because in the past, when you're doing equations of lines, we want fractions, we don't want decimals, but this is a real world example. So you may have decimals as a slope and or as the y-intercept, and that's okay. From here, the line of best fit, the point of using a line of best fit is making some sort of prediction. If this is how many houses are sold up to this point, what do I think the prediction is going to be in the next 3 years or 5 years or 20 years, whatever it is. And then you're going to look at your equation and you're going to decide, including with the prediction, does it seem reasonable? Does the slope seem like it's about okay? Does the y-intercept, again, seem like it's about okay? If your y-intercept is 250 and it looks like the graph is 270, that's fine. It's a line of best fit. We're doing the best we can. But if your equation of your line has a y-intercept of 250 and you look in the graph and it looks like it's 20, then you were off somewhere, you need to go back. All right, let's look at some examples here. We have a roller coaster. The table shows the largest vertical drop on 9 roller coasters in the United States and the number of years that they were opened. Identify the independent and dependent variable. Is there a relationship in the data? If so, predict the vertical drop in a roller coaster built 30 years after the date that they started taking advantage of this data. Okay. So first of all, the independent and dependent variable. Independent is always your x values. What's going on first? What's in charge here? The thing that's in charge is your years since 1988. So we're going to write that years since 1988. Always your x value is going to be your independent. Your dependent is going to be your vertical drop in feet. And that's going to be your y value. The correlation, which way does that trend seem to be going? It looks like it's positive. It's a positive trend. As x increases, y is also increasing. Now we're going to observe the line of best fit. Let's take a look at it. No one line will pass through all the data points. So we know even though these are kind of not on the line, that's okay. We try to go somewhere in the middle, do the best we can. Now, to make things easier and a little bit easier as a teaching tool, we're going to write an equation of line of best fit, but I use these points. So 2, 150, I approximated right there. And I also used 12, 300. Now notice the points I picked This 12,300 has a point there. Notice the point I picked there, 2,150. There's no point there, but that is pretty close to going through the corner of the box, so I decided to use it. So again here, you know how to find slope at this point. So again, if you need to pause this video so you can catch up or try it on your own and then see if you come up with the same answer I did. So by using my slope formula, I have 15 as my slope. Now, neither of the points that I started with up here are the y-intercept. So I'm going to use point slope form to get where I am. And I'm going to use some algebra and use point slope. So this is point slope. I'm going to get to my slope intercept form. So my equation of my line is y is equal to 15x plus 120. Now, again, I like to estimate. Let's go back and see how we did. Is my y-intercept 120? Well, it looks pretty close, right? That looks pretty good. And my slope is 15. So again, did I go up 15 over 120? I'm sorry, up 15 over 1. It looks pretty good. I mean, it's kind of hard to tell. We're guessing, but that's certainly not an unreasonable slope. So I'm going to say we're probably okay. So let's look at step 4. Predict the vertical drop in a roller coaster built 30 years after 1988. Now, again, we're noticing as years go up, then so is the vertical drops. I guess the technology is better and we know what's going on. So I'm going to substitute 30 years after 1988. Substitute that. Now, sometimes they'll just say, you know, they'll give you a year in itself. They'll say, you know, 2020 or 2022, what's the prediction? And then you have to figure out how many years from the start date, in this case is 1988, you get. Okay, so I get 570 feet when I substitute that in. So that's going to be somewhere. We're 30 years. We're going to be up here somewhere. That seems pretty reasonable. Okay, so we know I'm predicting the vertical drop is going to be 500. Oh, what's going on here? 570 feet. Now, the last question, is your equation reasonable? And we already checked that, the slope and the y-intercept. Yep, we think we are pretty good. One more thing just to look at too is our slope is 15. Remember that slope is our rate of change. So we're saying for every year that goes by, the vertical drop is going up 15 feet per year. So remember, rate of change is our slope. Okay, let's look at our last example. Use a scatter plot to find the approximate number of U.S. travelers to international countries in 1996. Write the slope-intercept form of the equation. The line passes through these points. Now, again, I picked points here just because as a teaching tool, it's a little easier if we all use the same points. So we're given this point right here. We're given another point up here. Again, you can pause the video, see if you can figure out what the slope is. I have 1051.7, so a little over 1,000 feet per year. Now, I could go to point slope if I wanted to, but remember, I could go right to slope intercept form because I have the y-intercept there. So I have y is equal to 1051.7 x plus 44,623. Now, we know that's our y-intercept in that case, they tell us, and it looks like for every year that goes by, we have a little bit more than 1,000 travelers that are traveling to international countries.